In example 8 and example 9, we have two examples of trickier substitutions. The general process here is going to be identical, but these problems are going to be a little bit trickier because our substitutions aren't going to swap out quite as nicely. We're not going to have exact statements for exact statements, but we'll see that in a second. We'll start off the same way. We'll identify our interior function, in this case 1 plus s to the ninth. So that will still be our expression for u. So we'll look at taking the derivative of that statement. So du over dx is going to be equal to the derivative of 1 plus s to the ninth, which will be 9s to the eighth, which means du will equal 9s to the eighth, and I should be using a ds there, not a dx. So du is going to equal 9s to the eighth ds. So if we look at the expression that we have here and the original problem, we see that we have the s to the eighth and we have ds. So for du, we can only swap in for this chunk. So we have to do something with this 9 because the 9 isn't anywhere in this original problem. So what we'll do is divide that 9 over to the other side to get du over 9 equals s to the 8 ds. So now we have s to the 8 and ds, and we can swap those with du over 9. So this is that idea where things are getting trickier. We're not just swapping in du, we're swapping in some slightly more complicated expression. We have to manipulate this statement a little bit more to get something so we can make that substitution. So our integral will become the integral of u to the 7th times du over 9. Now we also have some properties that will allow us to rework this. So this divided by 9 is the same thing as 1 multiplying by 1 over 9. Since that's just a constant multiple, we can pull that out front and write this as 1/9 times the integral of u to the 7th du. So this will become 1/9 times the integral of u to the 7th will be u to the 8th over 8 plus some constant c. So multiplying our denominators together and swapping back in for u, we'll get 1 plus s to the 9th to the 8th power over 72 plus some constant c. So again, what we did, all the steps were almost completely identical here. The one thing that changes is just this substitution for du. When du is set equal to something on the right and we don't have that exact expression in our problem, we have to divide something back over to the other side in order to get it equal to whatever the remainder of that problem is. So we'll look at one more example here. We've got our interior function, 7 plus e to the 5x. So we'll let that be our expression for u, which means that du over dx will be the derivative of that, which will be e to the 5x times the derivative of 5x, so times 5. Or, just to reorder that, we'll write it as 5 e to the 5x. That means du will equal 5 e to the 5x dx. So now we want to look at this statement and see what we have in the original problem to swap out. In this case, we do have the e to the 5x and the dx, but we don't have the 5. So again, we'll divide that back over to the other side to get du over 5 equals e to the 5x dx. So now in place of the e to the 5x and the dx, we can swap in du over 5 to rewrite our integral as the integral of u squared times du over 5. And then again, recognizing that dividing by 5 or multiplying by 1/5, that's just a constant multiple. So we can bring that out front and just write this as 1/5 times the integral of u squared du. So this will become 1/5 times the integral, or times u cubed over 3 plus some constant c. So swapping back in the 7 plus e to the 5x, we get 7 plus e to the 5x cubed over 15 plus some constant c.